Hello everyone, welcome back. I'm here with my new video on IB thermal physics, topic 3.2, modeling a gas. So let's go over the lesson objectives. The main lesson objectives for this topic are pressure, that's number one, pressure. Equation of state for an ideal gas, so we'll be talking about ideal gases and real gas. A kinetic model of an ideal gas, so it's about the ideal gas and how the particles move inside an ideal gas. We'll be going over the mole, the molar mass, and the Avogadro's constant. We'll be talking about the difference between real and ideal gas. Now, the differences between real and ideal gas, that's a very important question for IB exam. So make a note of that. As far as mole, molar mass, and Avogadro's constant is concerned, you get several numerical questions asked in IB based on mole, molar mass, and the Avogadro's constant. What are the applications and skills? Well, you should be able to solve problems using the equation of state for an ideal gas and gas laws. You should be able to sketch and interpret graphs, state of an ideal gas on pressure volume graph, pressure temperature graph, and volume temperature graphs. Sorry. Then lastly, you have to do one lab where you will be investigating at least one gas law experimentally. So it could be whether it's a Charles law or the Boyle's law, one of those gas laws we will be doing experimentally. Now let's look at the data booklet reference. You have four formulas that are given in the data booklet. Number one, that's pressure. P is F over A. That's pressure is force over area. N here stands for the number of moles. Number of moles is equal to the number of particles divided by the Avogadro's number. Then you have pressure times volume is equal to the number of moles times R, that's a gas constant, which is 8.31 multiplied by the temperature. Then you have the average kinetic energy, which is 3 over 2 times the Boltzmann constant multiplied by the temperature, or it could also be equal to 3 over 2 times R, which is the gas constant, divided by the multiplied by the temperature and divided by the Avogadro's number. Now, here we'll be talking about ideal gas and real gas. So we have one TOK question. When does modeling of ideal situations become good enough to count as knowledge? So when we'll be talking about real gases and ideal gases, and we'll try to compare how close are real gases to ideal gases. We will try to have a quick discussion on this topic. Now, let's try to understand the definition of pressure. So what is pressure? Pressure is actually force over area. So how much force is acting per unit area? That is called pressure. And the unit for pressure is, if you see, pressure is force over area. So force is in newtons, area is in meters square. So the unit for pressure would be force per unit area. And that's Newton meter square, Newton divided by meter square, and 1 Newton over 1 meter square, that's 1 Pascal. So pressure is force over area. You can think this way: if these molecules are striking the walls of the container, how often they hit the walls of the container, that determines the pressure inside the cylinder. So if the molecules strike more often to the walls of the container, the pressure is going to be high. If they strike less often, then the pressure is going to be low. So you can think in this way that if the temperature increases, the average kinetic energy increases. So if the average kinetic energy increases, it means that the molecules are going to hit the walls more often, and hence the pressure is going to be more. Now let's look at one numerical problem. You have the formula on the top. Pressure is force over area. So you have 150 kg man stands on 1 foot on some ice. Given that his foot is 9 centimeters by 10 centimeters in rectangular cross section, you are asked to calculate the pressure on the ice. So you know that pressure is force over area. So the first thing you need to do is calculate the force. You know the mass of the man. So mass times gravity would be the force. So you could calculate the force acting here, and then you could calculate the area. So area is 9 centimeters by 10 centimeters. Convert these centimeters to meters, and you will get the area. And then you can use this formula, and you could get the pressure. So if you see here, first we could calculate the force. A force is mass times gravity, which is 150 times 10, which is 1500 newtons. You should be using capital N here. This is a typo error. So Newton is represented by capital N. And then you find the area. So area is, you multiply this, convert this into meters. So you have here 0.09 meters multiplied by 0.10 meters, and that gives you 0.009 meters square. And you have the area now. And then finally you do pressure, which is force over area, and you will be getting your answer approximately as 170,000 Newton per meter square, which is 170,000 pascals. So remember the formula, pressure is force over area. Now you could get a question where you might have the pressure, and you might be asked to calculate what would be the area. So if you have a question like this, where if the ice is thin enough that will break under a pressure of 1 times 10 raised to the power 5 pascals, what should be the area of the shoe that will prevent, snowshoe, that will just prevent him from breaking through when on 1 foot. So they want you to find the area. The mass of the person is still the same, it's the same person. So area is force over pressure. So force is the same force, you have to use the same force as that from the previous question. So you see it's 1500 newtons divided by the pressure, which was 1 times 10 raised to the power 5. And when you solve it, you get approximately 0.015 meters square. So that's the first lesson objective, pressure is force over area. Now we'll be talking about an ideal gas. So these are the characteristics of an ideal gas. The molecules that make up an ideal gas are perfect identical spheres. They are perfect identical spheres. Their collisions are perfectly elastic. It means that the momentum and kinetic energy both are conserved when they collide with each other or when they collide with the walls of the container. Number 3, they have no intermolecular forces. So there are no intermolecular forces between them. Their potential energy do not change because intermolecular forces, they determine the potential energy. They are so small that the volume is much smaller than the volume of the container. So the volume of these molecules, they are much smaller than the volume of the container. So these are the characteristics of an ideal gas. And an ideal gas is technically an imaginary gas. It just exists on pen and paper. It's a theoretical gas. And this gas is used to model real gases. So we use this gas to model real gases. So these are the characteristics of an ideal gas. You're supposed to know this. Important IB question. Usually they start a question on topic 3.2 with a question which states that state the difference between an ideal gas and a real gas. So you are expected to know these 4 characteristics. Now have a look how temperature affects pressure. Now, if you see temperature, if you revisit the definition of temperature, temperature is average kinetic energy of the molecules. Now, when you're talking about low temperature, the molecules are moving slowly. medium temperature, the molecules are moving a little bit faster. And when you have a high temperature, the molecules are moving really fast. Now, when the temperature is high, you see the molecules collide with the walls of the container more often compared to when the temperature is low. So you can say that when the temperature is high, the pressure is also high. The important thing is pressure is determined by how often and how fast do the molecules collide with the walls of the container. Here you see, obviously, because the molecules are moving faster, they collide more often and they collide with greater velocity. So as the temperature is high, the pressure is high as well. Again, the same thing. So pressure will increase if the temperature will increase. Try to look at the simulation. You see this is low temperature and you can see the molecules moving slowly. If you see the medium, they are moving a little bit faster than the low ones. And if you're looking at the high temperature, they are moving way faster than the medium and the low ones. So as the temperature increases, the pressure increases as well. Now, how does the volume of the container affect the pressure? Now, if you see, if you have a smaller volume compared to larger volume, the molecules that hit the walls of the container more often when the volume is smaller. And in fact, the molecules are, since hitting more often, they are colliding and again, they are hitting. So it's the number of hits per second is way more than the number of hits per second in case of a large volume. So if the hits per second are more, that means the pressure is going to be more. So if the volume is smaller, the pressure is going to be smaller. If the volume is larger, the pressure is going to be larger as well. So the important thing here we studied was, what is the definition of pressure? Pressure is force over area. You might get some numerical problems on pressure formula, force over area. Then how does temperature affect pressure and how does volume affect pressure? Next class, we'll be talking about mole and the molar concept. See you in my next video.